Doesn't it feel as if we are standing on the threshold of something enormous, something capable of rewriting our understanding of the solar system itself? A quiet sense that humanity may not have been as alone in the universe as we once believed. For decades, space felt hostile, silent, indifferent. A vast darkness where life seemed like a rare accident, confined to one fragile planet. But what if that picture is incomplete? What if the silence of space is not emptiness, but simply unanswered questions? Right now, the direction of those questions points unmistakably toward Mars. Not the romantic Mars of ancient mythology, and not the dusty red dot seen through backyard telescopes, but a specific place on its surface, a vast, ancient scar known as Jezero Crater. This is not coincidence. Jezero was chosen with extreme care because it sits at a geological crossroads. It lies on the boundary between an ancient plain and an older, elevated region, a place where the planet's past may have been preserved rather than erased. For 4 years, a robotic explorer named Perseverance has been working there. And its name is not symbolic, it is literal. Day after day, meter after meter, the rover advances across terrain that has not been touched for billions of years. No rush, no shortcuts, just patient observation, careful measurement, and an almost stubborn refusal to overlook small details. Because on worlds like Mars, the smallest details can carry the biggest truths. Why Jezero? Because long before Mars became the frozen, radiation-scoured desert we see today, this crater was likely filled with water, not briefly, not seasonally, but for a geological stretch of time long enough to matter. Based on geological reconstructions, scientists believe that Jezero once hosted a lake with a drainage basin covering roughly 17,000 square kilometers. Water flowed into it through channels, slow, settled, and deposited sediments layer by layer. The crater itself is immense, nearly 49 kilometers in diameter, with depths reaching 2.7 kilometers near its center. To truly imagine this ancient lake, imagination must be restrained, not exaggerated. This was not a shallow pool evaporating under a weak sun. It was a stable system, water arriving, circulating, interacting with rock, and quietly recording its own history in stone. And stone remembers. On Earth, some of the most ancient traces of life are preserved not in bones or shells, but in sediments, fine layers laid down gently in water, protecting chemical and structural signatures across unimaginable spans of time. Jezero fits that pattern disturbingly well. Perseverance was designed specifically to interrogate such places. It carries spectrometers that read the elemental fingerprints of rocks, ground-penetrating radar capable of peering beneath the surface, environmental sensors tracking modern Martian wind and dust dynamics, cameras that resolve textures so fine they reveal how a rock formed, grain by grain. There is even a high-precision scanning system that turns an ordinary stone into a dataset dense with chemical and structural information. Alongside the rover operates a small helicopter Ingenuity, which proved that powered flight is possible in Mars' thin atmosphere, extending the rover's reach and scouting terrain ahead. But all of this hardware serves a single, focused purpose: to answer whether Mars was ever capable of supporting life. And the early answers were unsettling in the best possible way. Perseverance confirmed that Jezero is not merely an impact crater. The evidence points overwhelmingly toward a genuine ancient lakebed. Channels carved by flowing water are still visible. Sedimentary deposits match what scientists expect from long-term aquatic environments. In other words, Mars once had stable liquid water on its surface. That alone forces a shift in perspective, because water is not just a convenience for life as we know it. It is a chemical stage, a medium where complex reactions can unfold. where molecules can assemble, break apart, and reassemble into something more ambitious. Then came a discovery that sharpened global attention. Organic molecules, carbon-containing compounds were detected within rocks on the crater floor. This does not mean life has been found. Organic chemistry does not require biology. Such molecules can form through purely abiotic processes, but context matters. Organic molecules found in isolation are interesting. Organic molecules found in ancient lake sediments are provocative, because on Earth, that combination often accompanies environments where life either existed or could have existed. Yet perhaps Perseverance's most important achievement is quieter and less cinematic. Sample collection. Mars is covered in geological material that reads like an alien museum archive. Each rock is a record of conditions that once existed. Temperature, pressure, chemistry, water presence. Perseverance doesn't just look at these rocks. It catalogs them, studies them, seals selected samples with the explicit intention that one day they will be brought back to Earth for analysis in laboratories far more capable than any rover. This is a slow science, but it is irreversible science. One early example captured scientific attention: a small, oddly textured rock nicknamed Hedgehog. Even in images, it looks different. Its surface bears the marks of long-term erosion, as if shaped patiently by forces acting over extended time rather than sudden impact. At roughly 20 centimeters in size, it is modest, yet its uniqueness is striking. Similar rocks were absent from nearby terrain. Surrounding stones appeared smoother, more uniform. Hedgehog looked worked over by wind, by water, or perhaps both. Some researchers suggested it could be a remnant of sedimentary deposits left behind when the lake still existed. If so, it becomes more than a curiosity. It becomes a candidate, an object worth interrogating for biosignatures. Today, Mars is a cold, dry, unforgiving world. Radiation floods its surface. Liquid water cannot persist openly. Life, as we know it, would struggle to survive there now, and yet, astrobiologists continue to repeat an uncomfortable truth. Planetary climates change. On Earth, habitable periods have come and gone, sometimes lasting hundreds of thousands or millions of years. Mars may have experienced similar windows. If warm, wet conditions persisted even for 100,000 years, that is not trivial. That is time enough for chemistry to organize itself. Time enough for environments to stabilize. Time enough for something small, simple, and microbial to emerge if the conditions allowed it. This is why Jezero Crater matters so deeply. It is not just a location on Mars. It is a test of our assumptions about solitude in the universe. If Mars, our nearest planetary neighbor, was once habitable, then the question is no longer, are we alone? It becomes something far more unsettling. If life could arise there, how common might it be elsewhere? As Perseverance continued its slow journey across Jezero, one truth became impossible to ignore. Mars is not simple. It is not a planet with a single story, a single origin, or a single geological identity. It is layered, contradictory, complex. Some rocks speak the language of fire, others speak the language of water, and many speak both at once. This is where Jezero becomes scientifically dangerous in the best sense of the word, because the crater is not a clean narrative. It is a collision zone between different planetary histories, volcanic processes, sedimentary processes, transported material, chemical alteration, erosion, water interaction, all of it overlapping, all of it preserved, One group of rocks that captured attention were basaltic formations, later given the name M-as, a term drawn from the Navajo language, commonly used in mission nomenclature. Basalt usually tells a clear story. It forms when molten material cools and solidifies. Lava flows, volcanic activity, heat, pressure, fire-made stone. On most planets, basalt is a signature of internal geological energy, but Jezero refuses to be simple, because basalt can also travel. It can erode from highlands. It can be carried by water. It can be deposited in lakebeds and preserved for billions of years. So the same rock can tell two radically different stories depending on its context. When Perseverance analyzed these formations using its integrated high-resolution instruments, something critical appeared: clay minerals. Clay does not require life, but it almost always requires water. It forms when water interacts with rock over time, altering its chemical structure, transforming minerals, and embedding a history of liquid presence into the stone itself. So, when basaltic material contains clay inclusions, the narrative changes. Fire alone did not shape this rock. Water touched it, worked it, rewrote part of its structure. This pattern repeats again and again across Jezero. Volcanic origins, followed by aqueous alteration, igneous formation, followed by sedimentary transformation. Heat first, water later. It suggests a Mars that did not simply cool and die. It suggests a Mars that evolved, a Mars that changed states, a Mars that passed through multiple environmental phases, each leaving its signature in stone. Some of the most revealing discoveries weren't dramatic looking at all. Shortly after landing, Perseverance examined rocks located just meters from its touchdown point. Visually, they seemed unremarkable: dark stone, pale inclusions, subtle contrasts. No cinematic shapes. No obvious strangeness, just rock. But science thrives in the ordinary, because small visual anomalies often signal deeper chemical stories. The pale inclusions, embedded in darker material, hinted at changes in crystallization processes, chemical environments, or later stage alteration. Even these early samples raised the same core question: were these rocks shaped primarily by volcanic forces, or were they later transformed by water? This tension defines Jezero. Two versions of Mars competing for dominance in the evidence. Volcanic Mars, a world driven by internal heat, lava flows, and igneous geology. Watery Mars, a world shaped by rivers, lakes, sedimentation, and long-term water activity. And Jezero sits exactly where those worlds collide, which makes it the perfect place to search for life's prerequisites. But here is the deeper problem. Even if Mars had water, even if it had lakes, even if it had long habitable periods, that still does not guarantee life, because life is fragile and time is cruel. Heat destroys molecular structures, radiation breaks chemical bonds, oxidation erases delicate patterns. Geological recycling overwrites history. So the real scientific challenge is not only to find rocks formed in good conditions, but to find rocks that were preserved in good conditions. This is why Perseverance's mission design matters so much. It is not hunting for a single miracle object. It is building a contextual map. Where did this rock form? What happened to it later? Was it heated? Was it submerged? Was it buried? Was it protected from radiation? Was it chemically altered after formation? Each rock becomes a timeline, an object. And this is where the mission becomes bigger than Mars itself. Because Perseverance is not only exploring. It is preparing for the future. The rover is sealing selected samples in specialized containers with one explicit purpose: return to Earth, not tomorrow, not next year, but eventually. This transforms the mission from exploration into archival science. Mars is no longer just being observed, it is being preserved, cataloged, stored, prepared for decades of laboratory analysis using technologies that don't yet exist. This is slow science, but it is irreversible science, because once those samples are on Earth, they will be examined by generations of scientists, with instruments far more powerful than anything that can be sent to Mars: isotope analysis, nanoscale imaging, molecular spectroscopy, techniques capable of detecting patterns too subtle for current tools. If Mars ever hosted life, even microbial, even primitive, those samples are our best chance of proving it. And yet, beneath all of this technical effort lies a philosophical shift that is harder to measure, because Jezero is changing the way we think about planetary identity. Mars is no longer just dead. It is transformed. It is not a failed Earth. It is a planet that passed through multiple evolutionary phases and ended in a state of collapse. That alone reframes the question of life, not as something exclusive to Earth, but as something that may emerge wherever conditions briefly allow it. Jezero does not promise answers, but it destroys the old certainty of emptiness. It replaces silence with ambiguity, desolation with complexity, loneliness with possibility, and as perseverance continues its slow movement across that ancient lakebed, one idea becomes harder and harder to dismiss. Mars was not always a desert. Mars was not always hostile. Mars was not always dead. And if it once lived, even briefly, even quietly, even at a microbial scale, then the universe itself becomes a very different place. Then Mars did what it does best. It complicated everything. In March 2025, Perseverance encountered a rock that immediately broke the visual rhythm of Jezero Crater. It didn't look like the others. It didn't behave like the others. And it certainly didn't fit neatly into any single explanation. Later, it received a name inspired by Earth: St. Paul's Bay, because of romance or tradition, but because of implication on Earth. St. Paul's Bay is associated with shipwrecks, drifting, survival against odds. On Mars, the name carried a quieter suggestion. This rock may not belong where it was found. Its texture was unsettlingly unfamiliar. Clusters of small, rounded spheres pressed together into a single mass. Not smooth like lava, not layered like sedimentary slabs, but something in between. To many observers, it resembled frog spawn. Others thought of berries turned to stone. Still, others compared it to grains of popcorn fused together under pressure. Metaphors are dangerous in science, but patterns are not, and this pattern demanded attention. Why? Because spherical structures are rare for a reason. They do not form easily, and when they do, they usually require very specific conditions. On Earth, similar textures often form in environments where water plays a central role. Groundwater moving slowly through rock, minerals precipitating over time, chemical reactions repeating again and again. How spheres emerged naturally. When Perseverance revealed this rock in Jezero, questions multiplied instantly. Was it formed here, or was it transported? Nearby stood a rise in the terrain with a name pulled straight from folklore: Witch Hazel Hill. Orbital data showed dark material near its crest, material that looked suspiciously similar to the strange rock below. one hypothesis quickly gained traction: the stone may have originated higher up and rolled or been carried down into the crater basin. True, that changes everything. Because a transported rock is a messenger. It carries information from environments the rover has not yet reached, from geological contexts hidden beyond its wheels, and which Hazel Hill itself is no ordinary bump in the landscape. Roughly 135 meters high, it exposes multiple layers of Martian history stacked vertically. Each layer corresponds to a different era, a different climate, a different chemical reality. In places like this, impacts, erosion, and gravity work together to pull deep material closer to the surface. Natural excavation, planetary archaeology without tools. Back on Earth, scientists immediately searched for analogs, and they found them. Certain forms of hematite iron-rich minerals form spherical textures when groundwater interacts with rock over long periods. Similar formations exist in sedimentary basins in Australia. Others appear in Jurassic sandstones in Utah, USA. None of this proves the Martian rock formed the same way, but it proves something equally important. Nature knows how to make these shapes in wet environments. That alone keeps the most uncomfortable door open. Then came another discovery, more subtle, more controversial, and far more dangerous to ignore. In July 2024, within an ancient river channel inside Jezero Crater, Perseverance encountered a rock with a surface pattern that earned it an informal name: leopard spots. Dark circular markings, lighter surrounding material, irregular but structured, not random. At first glance, it looked like a curiosity. At second glance, it looked like chemistry. Later analysis revealed something startling. The dark rings were rich in iron and phosphates. The lighter regions contained sulfur, calcium. Sulfate was present throughout the structure, and suddenly, Mars crossed a line, because on Earth, structures with that exact chemical combination are often linked to microbial activity. Microbes alter their environments. They drive redox reactions. They change iron states. They precipitate minerals. They leave behind patterns that chemistry alone rarely reproduces. So precisely, this does not mean microbes were found, but it means the rock behaves the way microbially influenced rocks behave on Earth. That distinction matters. Then came the complication, because Mars always adds one. The same rock showed signs of association with high-temperature volcanic processes, minerals that typically form under intense heat, conditions hostile to delicate biological structures, which raise the uncomfortable possibility: what if the patterns are not biological at all? What if they are chemical echoes of volcanic activity? This is where public headlines and real science diverge. Science does not ask, is this life? Science asks, what sequence of events could create this exact outcome? And sometimes the answer is not singular. A rock can be born volcanic, altered by water, reworked chemically, exposed to heat, then buried again. Mars has had billions of years to complicate its own evidence. Yet despite the uncertainty, two independent research teams stated something unprecedented. This rock represents the strongest evidence yet for past habitability and possibly biological processes on Mars. Not proof, but pressure. Pressure on old assumptions. Pressure on the idea that Mars was always sterile. Pressure on the belief that life is rare simply because it is fragile. Jezero Crater now looks less like a simple lakebed and more like a collector of contradictions. Volcanic, rocks altered by water, sedimentary, deposits overprinted by heat, transported stones carrying Stories from distant environments. Chemical patterns that mimic life, too closely to dismiss casually. Without life, the puzzle feels chaotic. With life, even microbial, even extinct, the puzzle suddenly gains coherence. That does not mean the answer is yes. It means the answer is no longer, obviously no, and that single shift changes everything. Because if Mars smaller, colder, or less protected than Earth could briefly support life, then life may not require perfection, only opportunity. And opportunity, it seems, once existed on the red planet. For decades, the idea of hidden oceans belonged to distant worlds, Europa, Enceladus, moons wrapped in ice, far from the sun, where liquid water hides beneath frozen shells. Mars was never part of that club. Mars, we were told, lost its water. It bled it into space. What remained froze into polar caps or vanished into dust. Then insight changed the conversation, quietly, almost accidentally. From 2018 to 2022, the InSight lander sat motionless on the Martian surface, doing something no rover could do properly. It listened to Mars itself, using ultra-sensitive instruments. InSight recorded Marsquake's vibrations rippling through the planet's interior. Just like on Earth, seismic waves behave differently depending on the material they pass through. They speed up, slow down, bend, scatter. By analyzing those subtle changes, scientists can reconstruct what lies beneath the surface without ever digging a hole. And what InSight detected was unexpected. At depths between roughly 10 and 20 kilometers. Seismic waves pass through a layer whose behavior closely resembled that of water-saturated material, not ice, not dry rock, but something mechanically similar to environments on Earth where pores and fractures are filled with liquid. The implication was staggering. Mars may still hold enormous reserves of water trapped deep beneath its crust, not lakes, not seas, but a planet-scale sponge of fractured rock soaked with liquid water. If correct, this discovery reframes Mars entirely. Water would not only be a memory of the past. It would be a hidden feature of the present. And with water comes a question that refuses to stay buried. Could life survive there? The Martian surface today is brutal. Radiation pours down unhindered by a thick atmosphere. Temperatures swing wildly. Liquid water cannot remain stable, but underground, conditions change. Rock provides shielding. Temperatures stabilize. Radiation weakens. And if water is present, chemistry can continue quietly at sea, protected from cosmic violence. On Earth, we know this story well. Life thrives in deep subsurface environments, kilometers beneath the surface, inside rock fractures, feeding on chemical gradients rather than sunlight. Even in the Mariana Trench, nearly 11 kilometers beneath the ocean surface, life not only exists, it flourishes. Darkness, crushing pressure, near freezing temperatures, and yet ecosystems persist. Humans have been there, observed it, documented it. So when we ask whether Mars can host life underground, the honest answer becomes uncomfortable. Why not? If Mars ever developed life during its wetter past, retreating underground may have been the only way to survive planetary collapse. Surface dies, subsurface endures. This possibility alone makes Mars more than a dead world. It makes it dormant. But Mars is only the beginning of a much larger question, because once you accept that life may not be rare, you are forced to ask something deeper. What kind of universe allows this? Was life inevitable or accidental? Is our universe a one-time event, or part of something repeating? The dominant model of cosmology tells a familiar story. The universe began in a hot, dense state, a singularity. Then expansion, galaxies forming, stars igniting, planets assembling. It explains much, but not everything. What exactly is a singularity? Infinite density, infinite temperature, or place where mathematics stops behaving. Even physicists admit that singularities are not explanations, they are warnings. Alternative ideas exist. One family of theories proposes a cyclic universe. Expansion does not continue forever. Eventually, it slows, stops, reverses. Galaxies drift back together. Stars collide. Black holes merge. The universe collapses into another singular state, and then rebounds. A big bounce instead of a big bang. In this view, our universe is not the first, nor the last. It is a phase, a chapter, a cosmic reincarnation. The appeal is obvious. Death is not final. It is transition. But observations complicate the story. Measurements of distant galaxies show that expansion is accelerating, not slowing. Dark energy appears to dominate, which suggests a different fate. Not collapse, but separation. Expansion continues unchecked. Structures begin to tear apart. First galaxy clusters, then galaxies, then solar systems. Eventually, even atoms lose coherence. This scenario is known as the Big Rip. In such a universe, time stretches endlessly forward, but interaction dies. Light from distant galaxies fades beyond the cosmic horizon. Stars burn out. Matter decays. After hundreds of billions of years, the night sky would go completely dark. No stars. No galaxies. Nothing to observe. Even black holes would not survive forever. According to Hawking radiation, they would slowly evaporate, leaking information back into space. What remains is almost nothing. Elementary particles drifting through near perfect emptiness. A universe approaching maximum entropy. But here's the twist. Even in near absolute emptiness, physics does not completely shut down. Quantum fluctuations still occur. Tiny disturbances, momentary blips in the vacuum. Some theories suggest that, given enough time, these fluctuations could assemble something extraordinary. Boltzmann brain, a self-aware structure arising spontaneously from chaos, complete with memories, thoughts, consciousness. The probability is absurdly small, but infinity is patient. In some models, infinite time makes the improbable inevitable, which raises a disturbing question. Could such a mind become the seed of a new universe? Could consciousness itself restart reality? Speculation, yes, but not meaningless speculation. Because when cosmologists explore eternal inflation, the universe fractures into regions, mini-universes budding off from a larger cosmic structure, each with different physical laws, different constants, different outcomes. A multiverse. In such a framework, life is not special because it is rare. Life is special because it is selected. We exist in a universe where conditions allow observers, because only such universes can be observed at all, which circles back to Mars. If life emerged there, even briefly, even underground, then life is not a miracle. It is a tendency, and tendencies do not stop at one planet. Mars stops being a graveyard. It becomes a warning, a glimpse of Earth's possible future, a world that once had water, energy, opportunity, and lost it. Understanding Mars is not only about finding alien life. It is about understanding ourselves, our fragility, our timing, ice in a universe that may recycle itself endlessly, or tear itself apart slowly, or spawn realities beyond imagination. Mars does not answer these questions, but it forces us to ask them, and once asked, they do not let go. At some point, every exploration reaches a boundary, a wall you can touch, but a limit to what can be seen directly. In cosmology, that boundary has a name. The zone of avoidance. It sounds almost poetic, and in a way, it is. For centuries, astronomers noticed something unsettling. Wherever they pointed their telescopes, the universe appeared crowded. Galaxies, clusters, nebulae, quasars, everywhere except one place, along the plane of the Milky Way itself. There, the sky seems strangely empty. As if a massive piece of the cosmic puzzle had been erased. This anomaly was first formally described in 1878 by astronomer Richard Proctor, while studying star catalogs compiled by the Herschel family. He noticed a systematic absence of extragalactic objects in a specific band of the sky. At first, the explanation seemed simple. Dust, gas, obscuration. The dense disk of our own galaxy blocks our view, and indeed, about 20% of the extragalactic sky is hidden from optical observation when viewed from Earth. But simplicity never survives scrutiny for long, because emptiness is rarely empty. As technology improved, astronomers learned how to see without seeing. Infrared, wavelengths, radio astronomy, X-ray, and gamma-ray observations. For radio waves, especially those at the 21-centimeter hydrogen line, the Milky Way is almost transparent. When astronomers finally looked through the galactic veil, they found it structured. The first breakthrough came with the discovery of Dwingelu 1, a spiral galaxy roughly 10 million light-years away in the constellation Cassiopeia. Then came Dwingelu 2, its smaller, irregular companion. Later, infrared surveys revealed additional galaxies lurking behind the dust, including dwarf systems previously invisible to optical telescopes. The zone of avoidance was not empty. It was crowded, and hiding something far larger. As surveys expanded, astronomers realized they were not merely uncovering isolated galaxies. They were uncovering architecture, vast, organized structures on a scale that defies intuition. Among them stood one of the most unsettling discoveries in modern astronomy, the Great Attractor. Not a monster, not a singular object, but a gravitational anomaly, located roughly 250 million light-years away. The Great Attractor exerts a pull so immense that entire galaxy groups, including our own, are drifting toward it at speeds approaching 600 kilometers per second. Its mass is estimated to be equivalent to tens of thousands of galaxies, and yet, it cannot be seen directly because it lies buried deep within the zone of avoidance. When astronomers finally confirmed its existence in the 1980s, they did so indirectly by measuring the peculiar velocities of galaxies deviating from uniform cosmic expansion. Something was pulling them hard. The Great Attractor is now understood to be part of a larger structure, the Laniakea Supercluster, our home supercluster within which the Milky Way itself resides. But even that was not the end of the story. Behind the Great Attractor lies something even more massive, even more incomprehensible. The Shapley Supercluster. Infrared and radio observations revealed its true scale only recently. Its mass rivals or exceeds that of Laniakea itself. Its diameter spans roughly 200 million light-years, and its gravitational influence amplifies the pull of the Great Attractor, shaping the motion of galaxies across vast regions of the local universe, within a radius of 1 billion light-years. No structure larger is known to exist. At this point, the universe stops looking random. It begins to resemble a cosmic web. Galaxies are not scattered like dust. They are arranged along filaments, walls, nodes, separated by immense voids. One of these filaments forms the Great Sloan Wall, stretching over 1.3 billion light-years, a structure so vast that imagining it borders on the impossible. Another, the Hercules Corona Borealis Great Wall, discovered through gamma-ray burst distribution, spans up to 10 billion light-years, making it one of the largest known structures in the observable universe. These walls are not solid objects. They are regions of slightly higher matter density, but on cosmic scales, slightly higher is everything. They formed early, from subtle density fluctuations after the Big Bang, amplified by gravity over billions of years. They are the skeleton of the universe, and the Zone of Avoidance hides some of the most critical bones. Why does this matter? Because to understand the universe, you cannot study only what is easy to see. You must confront what is hidden. Mars taught us that life may exist beneath surfaces. Cosmology teaches us that structure may exist beneath obscuration. The pattern repeats today, thanks to infrared observatories, radio surveys, and next-generation instruments like the James Webb Space Telescope. The Zone of Avoidance is no longer a blind spot, just a difficult one. Modern cosmic maps now include hundreds of thousands of galaxies, stretching nearly to the edge of the observable universe at 13.7 billion light-years. They show color, ocean structure. They show that emptiness is an illusion. And finally, the story circles back to us. Mars, the universe, hidden oceans, hidden galaxies, hidden structures. Every time humanity assumed something was absent, it turned out to be merely concealed. Life may not announce itself loudly. Structure may not reveal itself easily. Meaning may not appear where we expect it, but persistence changes the picture. Perseverance on Mars, patience in cosmology, listening instead of assuming. The universe is not quiet because it is empty. It is quiet because it is vast, and we are only beginning to learn how to hear it, not as silence, but as a pattern.